First off, if you take a look at my publications, you can see a lot of publication in the past on the census, but I kind of winding down the work on the census because now we get Democrats president in the White House. Okay. It's changed all the time. We got a lot of money in the past for the armies and the environment, but now we're going to move more to the health and energy application. So you can see my focus now are in these three areas: the cancer detection and treatment. And we still have some cancers here, and the green energy and new advanced materials for energy and the environmental applications. So just to show you a couple projects we have been working on, some progress here as well. The first is the prostate cancer treatment. We are working on the synthesis of small molecules. This is the structure of the molecule. That can complex with inhibits the enzyme called the PSA that then stop the proliferation of cancers, prostate cancers. So we've been working on this for several years, and then have been working on this for several years. I'll tell a little more details, about this work later. But here, we have synthesized, he has synthesized this compound with 13 derivatives, actually 20, but so 13 is a pure. He showed this, the IC50 of the compound binding constant. We have a couple compound bind pretty strong with the protein. After a lot of modeling work and synthetic work, now we're moving to we'll finish the binding constant measurement. And then we're going to work on cell assay and animal, hopefully, an animal test, and then eventually clinical trial. If any one of the compound can do the work, and then we're going to be millionaire or better. But if not, we go back to the ground zero and then remodel the compound and synthesize again, eventually for the cancer treatment. One project. Second, energy. Dr. Edison just mentioned it's the solar cells. We are working on a compound with this structure here. The idea about this, a couple of things, this molecule can absorb more sunlight, redshift to not only in the past it's a green, blue area, wavelength light, but also red area, so it can have a broad range of absorption. And in that case, you can only need the thin films other than thicker ones. It's going to be more efficient, and so conductivity is going to be better. And also, hopefully, we're going to design this molecule so the band gap match between the HOMO of those the conducting bands of the titanium oxide and the HOMO excited state of this molecule. All right, so we've been working on that for a couple of years. We're almost there. Noah have been working on this, and the compound, the ligand is almost there. Now we're going to make large quantities of that, and then complex with the racemium and test efficiency of that compound. The third is metamaterials. It's metamaterials means this invisible, equals this invisible cloak materials. So the idea is not really for the visible light, but we designed a system that can be invisible to the gigahertz wavelengths for the radar and for the stealthy airplane. That application. A lot of details, so I'm going to skip, but I have to skip this because of time. But once we have that works in the future, I'm going to show you. It's kind of exciting. And this is something new. I would like to spend a bit more time. We'll get some new interesting data on this, results on this also. This is an antibiotic solution treated by plasma. So we start with the water, but later we use many other materials, other liquids, other solutions as well. Just pure water, nothing in the water. After you treat this with plasma, it turns out to become a very powerful antibacterial solution. Antibiotic solution that can kill all the bacteria. We tried 100 bacteria, viruses so far. They killed everything, and pretty efficient. We also if we treat this with some amino acid solution other than pure pure water, it can be more powerful, a couple of times more powerful. And in the medical school, they also treat this urine. It turns out that it all works as well. So kind of nasty when you hear this, but what if the people working, the army working in Afghanistan, no water source, and the urine works fine for the hygiene? It turns out it's silly, but that works at least. Okay. And also we're trying to figure out now on the chemistry side, we're trying to figure out what's going on there, what's the cause this, what can make it so powerful. It's got to be some radicals. So we're trying to figure out from water what the radicals going to be. The couple radicals we have, hydroxide and hydroxy group, and a couple others, proxy, nitrate, and so on. But if we trace with valine, we get more different kind of particles that can kill penetrate the wall of the bacteria to kill that as well. So those are the mechanism from the valine, and it turns out that my postdoc spent a lot of time, and students as well spend a lot of time on this. Eventually figure out all the radicals formed and the intermediate and product from this direction contribute to that. Also, it's the kinetic of the valine and the sugars, a couple other things involved. It's a couple other solutions we use for this. That product can be involved to different areas from the pure simple water one plasma, but it turns out we get work on the plasma medicine and plasma for the environment and the plasma for energy. I'll show you one, two slides later. Here's another application with the plasma chemistry. This is antibiotics in the hospital. I'm not sure you're aware of that. The hospital, they turns out to dump all the antibiotic solution after treatment into the drain directly after treatment. The problem with that is some bacteria are gonna change. Eventually, there's some bacteria developed in the drain that's antibiotics. So then the antibiotic resist bacteria grow there. That's in the long term. That's a very big problem. So we need to do something about this. A lot of discussion on how to do this. Here's the efficient way we figure out. We only need to treat the plasma, this antibiotic solution 2 minutes, 2 seconds with the plasma. And turns out after 2 seconds, well, I showed you 2 minutes, 3 minutes for the mechanism study. But turns out only 2 seconds, the antibiotics there change that, so the bond break to something else. And well, this is the product after 10 minutes, but after 2 seconds, one bond in the full membrane that's going to break, and then that's not going to be antibiotics anymore, so you can dump at that time into the solution. So that's one application of this. And another interesting thing we saw this again, we work on this again, we found something even more interesting. Here is a ribose, and this is the moldy of the ribose work. So we treat the ribose with the plasma after a couple of minutes, and then we measure what's happened to the ribose. This is a solid state, not liquid. Liquid can decompose, but in the solid state, it becomes polymerized. We get the polyribose, okay? After a couple of minutes, it becomes polyribose. So what does that mean? How can that be useful? We thought, oh, we're going to work on this, add the phosphate in there as a backbone. How about we treat this with plasma? Can they form polymer like this? If it does, we make DNA, okay? I don't know. They're kind of crazy. We create life on this, okay? But that's the data is really convincing so far for that. Okay, but we'll work on this. I don't know the result yet. And I become more and more interesting about the plasma chemistry because it looks promising, more new data. And here's just one of our first paper submitted to JPC-B accepted. This is my second paper published as is. No need to change. So when you see that, always happy. Otherwise, the reviewer turns to having you all the time. Oh, it's terrible here and there. You're going to change this, but that's too. You don't need to change anything. As a matter of fact, it's not really. It's nearly as is. One reviewer said, "Oh, you need to add another amino acid to compare." I reply simply, "There's another paper." Okay, I really cannot add together. Too much work there. So that's nicely received by the reviewers, and we get some data. And we'll actually go back to this a little bit. So we got this application. Now we're working on. We get the proposal out. Hopefully get a grant soon, and to convert the natural gas to gas there. I don't know if that's going to be energy efficient or not, but as long as, well, so far it works. Okay, already we showed the process work. But how much energy, well, they're going to be cheaper. The price of the gas, this new gasoline, plasma gas is going to be cheaper than the one we purchased. Well, 87, 89, I don't know. Okay. Hopefully we'll get it over there somewhere. Um, Another project is with a medical school and engineers on the 3D printing. We printed this scaffold, and then on that scaffold, we build grow T cells. Okay, and then later when they dissolve the polymers, then we rebuild with the 3D printed structure to help the growth of the T cells, as the organs and T cell organs. Energy applications, we had lots of nanostructures for LED applications, hopefully, and solar cell applications. We'll be working on that. And then the interesting project is the MOF, organic hybrid. It's a material that's material that have lots of pores in the middle. That's typical morphology of this so-called MOF, metal organic framework. You see publication almost 100% publications. They show you this morphologies of this MOF. Only one I saw with nanowires. But we work on a similar procedure, modify the procedure, but instead of in solution, we work on this on the surface. Turns out we grew lots of these nanowires on the surface. Not really 10 nanowires, but nanowires standing on the surface. So we call them nano pillars, but it's the general structure of 1D structure of this materials there. Okay, we have two systems, zinc, two MOF system here. I should have a better image there. Oh, no, it's not here. It's a dense structure, kind of forest there, probably you see. Oh, it's a crystal structure of that, and some fluorescence image of that. And several applications you can find literatures on the nanopillars, but all inorganic ones, and metal and inorganic ones, for the light, fuel cell, or solar cell, and batteries, cell growth, photodetector, lasers, and so on. If you read the papers now, even you Google nanowires, you're not going to see nanowires. 80% or 90% of the papers is about the array, nanowire array, or in other words, nanopillars. And also the imaging and cell and so on. A lot of applications so far in many papers. And we're interested in this because traditionally, when in past years you see the nanopillars, they made this with the lithography approach of VCALS, thermal deposition, and some template. But we use this very simple approach, this self-assemble approach. You simply mix the two solutions on the surface, and then you can glue nanowires in a couple days. Just leave it alone. You don't need to do anything. Okay, so that's also first organic and inorganic hybrid materials. Nobody have published in that work organic ones. In the past, all the inorganic ones, and silicon and metals and so on. And even more, we have the pores in the middle, so I'm going to bring something more to play. So hopefully some talent student can help me to find a really big application of this. Okay. I need to thank all my talented, very smart, hard-working students, especially Ben, who did the most work in all this project, plasma, and synthesis of drug molecules and nanopillars. So that's him, I believe. Hard to see. That's the old picture. See how young you are at that time. That's 2 years ago, actually. But I need to get a new image. But thank them all. A lot of contributions from them. I'm looking for really talented students, undergrad, junior students, for the senior project in my group as well. Thank you all.